Okay, now that you've seen the first example of your non-deterministic finite automaton, let's take another look at another example and see how this machine works. This is a four-state machine. It starts in state q sub 1, so q sub 1 is your start state, and then for some states there are multiple outgoing transitions for some symbols. For example, q sub 1 has two outgoing transitions for symbol 1. Q sub 2 and Q sub 3 have exactly one outgoing transition for symbol 0 and for symbol 1, and Q sub 4 has no outgoing transitions. So effectively, when you end up in Q sub 4, if that is the end of your string, you accept. Otherwise, that thread of operation that ended in Q sub 4 will die after the next operation. So let's see what this machine does now and how it computes. Let's call this, then again, as we said in the slides, this is machine n sub 2. So what's going to happen for this machine if this machine sees a 0? So it starts in Q sub 1, over a 0 it stays in Q sub 1. And it's going to stay in Q sub 1 as long as it sees a 0. The moment the next symbol is a 1, then your machine will have two choices to go to. It's going to go to Q sub 2, or it's going to stay in Q sub 1 for reading a symbol 1. Now, in Q sub 2, if you see a 0 or a 1, doesn't matter. You go to Q sub 3, and in Q sub 3, if you see a 0 or a 1, doesn't matter. You're going to go to Q sub 4. So, but your machine will then for a 0, if you're in Q sub 1, you're going to stay in Q sub 1. But if it was a 1, this machine is going to go again split into Q sub 2 or Q sub 1. And this process is going to start every time you see a 1. So what is this process whenever you see a 1? What does this machine do? When it sees a 1, as you see here, these two outgoing transitions that give your machine a choice, it basically act as a guess. So every time your machine sees a 1, it basically guesses that this 1 is two symbols away from the end of your string. And if that was the case, then you accept. Now, if it were not the case, if after two symbols after the one that you guessed, you see another symbol, for example a 0, or a 1 for that matter, then since Q sub 4 doesn't have any outgoing transitions from there, then Q sub 4 operation dies, and the thread with it will die as well. Meaning that your guess is rejected, that you saw the end of your string and 3 symbols ago you saw 1. So if you want to look at this machine accepts all strings in which the third symbol from the end of the string is a 1. And but the thread of operation that stays in Q sub 1 is going to stay active. So then the next time you see another 1, you're going to split, guessing that you have seen the 1 that is 3 symbols before the end of the string, and over the next 2 symbols, this machine validates that. And if there were more than 2 symbols after this 1, then apparently the guess was wrong, and that thread of operation is going to die with it. So this is a nice example to show you the power of non-deterministic finite automata, and in fact the power of non-determinism compared to a deterministic finite automata. Remember, I told you that a deterministic finite automaton that performs the same operation as a non-deterministic one will have it may be the case that the deterministic automaton may end up having far more states than the non-deterministic one. And so I'm going to show you now what would be the way to write the deterministic version of this automaton and then show you how it is. In fact, the smallest DFA, deterministic finite automaton, that accepts the same string, effectively strings that have a 1 in the third location before the end of the string, is the smallest DFA is composed of 8 states. So let's go through this creation of our DFA and see how this machine, a DFA version of it, works. So I'm going to start with the Q sub 000, meaning that all I have seen so far has been zeros. So apparently I'm going to stay in this state as long as I see a 0. The moment I see a 1, then I'm going to branch this state into the state that it has a 1 at the rightmost location. So what's going to happen with this? If I go in, and from this point on, I have 2 choices to take. Either if I see a 0 or if I see a 1. So let's take the case with a 0. So I'm going to go to a state in which the symbols I've seen has been a 1 followed by a 0, and before them there would be a number of zeros. So I'm going to go to state Q sub 0, 1, 0. Then I'm going to come back to the transition for 1, the outgoing transition for this state, a little bit later. Actually, let's take the transition out of 1 here now. So if you're in Q001 and you see a 1, you're going to go into the state Q011. So let's go to the state Q010. From there, if you see a 1, you are going to go to state Q101. And of course, if you see a 0, you're going to go back, because you're just going to shift these letters to the left and then add the last symbol to them. So it's going to be 0, 1, 0 if you see a 0. So you're going to go back to your original state. What's going to happen if you see a 1 in this in the state Q101, if you see a 1, then you're going to go into this state here. Because apparently Q101, when you see a 1, you add a 1, and then you keep these, and then you discard that guy. So you're going to end up with Q011, and so you're going to go to Q011 down here. When we are in Q011, when we see a 1, we are going to go to a state in which we have seen 3 consecutive 1s. And then we're going to stay in this state as long as we keep reading 1s. And then if we see a 0 out of the state Q001, if we read a 0, then we are going to go into state Q110. Again, if you want to see what happens here, I'm in Q011, and then when I read a 0, then I'm going to keep these guys and I'm going to discard that, so it's going to be Q110. Now Q110, if you read a 0, if you read a 1 from there, right? So you're in Q110, and if you read a 1, you keep these 3, and then you discard this guy. So you're going to go back to Q101, and then if you do see a 0 from this state, then you're going to go into state Q101. 0. Again, you're in state Q110. If you see a 0, you basically keep the last 3 and then you discard the first one. So you're going to go to Q100. There's another state that takes you to Q100, and that is this guy. If you are in state Q010 and you see a 0, then you discard the first one, you put a 0 at the beginning. So over a symbol 0, Q010 goes out into Q011. I'm going to discard this also. Discard that. Perfect. And then my Q100 over a 0, it's going to go to the original state. Again, if you're in state Q100 and then you read a new 0, then you're going to keep these 3 and then you're going to get rid of the first one. So you're going to go back to Q00. And if you are in state Q100, so if you're in state Q100 and then you read a 1, keep these 3, discard that guy. So you're going to go back to Q001, which is right there. State Q111, also when you read a 0, if you're in state Q111 and you read a 0, you keep the last 3, you discard the first one, so you're going to go back to Q110. Okay, so now let's take a look and make sure that for every state we have one transition for 0 and one transition for 1. And to check that, I'm going to start with Q000. I have a transition for 0 and a transition for 1, so this is checked. I have Q001. I have a transition for 0 and a transition for 1. This is checked. Q010. I have a transition for 0 that goes all the way down here and a transition for 1. So this is checked. Q100. A transition for 0 and a transition for 1. This way. So it's transition for 1, transition for 0. That's checked. Q011. I have a transition for its 0 and a transition for its 1. So that's checked. Q111, I have a transition for 1 and a transition for 0, so that is checked. Q100, I have a transition for 1 and a transition for 0, so that is checked. And Q100, I have a transition for 0 and a transition for 1, so that is checked. So all my 8 states, and I have 8 states, state 1, state 2, state 3, state 4, state 5, state 6, 7, and 8. So all my 8 states are done, and as you see, oh, I forgot the accept states. Which one of these states are accept states? Remember, I need to accept all strings in which the third symbol from the end of the string is a 1. So all the states in which the third symbol from the beginning is a 1 are going to be accept states. So Q101 is an accept state. Q111 is an accept state. Q110 is an accept state. And Q11100 is an accept state. All of the states where the third symbol is a 1 are going to be accept states. So I have 4 accept states, 1, 2, 3, and 4. So my DFA here is going to be Q sigma delta Q sub 000 and the set F, where Q is going to be set of Q000, Q001, Q010, all the way to your Q111. Your sigma is the symbols 0 and 1. Your delta is this guy, which is from Q cross sigma to Q. Q sub 0 is going to be your start state, which is Q000, and then F is going to be Q100, Q101, Q110, and Q111. Well, obviously, this now should be clear to you that creating a DFA that accepts this string was actually far more efficient and far smaller in terms of the number of states than its counterpart. In fact, there's a theorem that I might actually give you um, as a homework assignment, that the maximum number of states that a DFA would have to recognize the same language as an NFA would be 2 to the n. The number of states in a DFA could be, in theory, 2 to the n, where n is the number of states in the NFA that recognizes a language. So, in other words, if an NFA with n states recognizes a language, let's say L, then a DFA recognizing the same language L could potentially have 2 to the n states. And so as you see, apparently DFAs are deterministic computation, and as such, they may require a lot more number of states than their NFA counterparts. NFA counterparts, because of the flexibility and the non-determinism, would allow us to simulate and to recognize a language potentially with far fewer transitions and number of states than we otherwise might require from an NFA. So this is the one example, and now we're going to go and check another example. Alright, so now let's take a look at another example. In this example, I have a state with an NFA with 6 states, and the language here, the alphabet, is a unary alphabet. It's only composed of symbol 0, and I'm also including epsilon transitions. And let's see what kind of language does this machine recognize. So apparently this machine starts from this state q sub 0, and then upon q sub 0, without reading anything, it takes the 2 epsilon transitions, epsilon to go to the upper branch and the epsilon to go to the lower branch. And notice that since I have 2 outgoing transitions at any given time, my machine basically performs a guess. It guesses to take the upper branch or to take the lower branch and see what's going to happen. So regardless of what branch it takes, it is going to be in an A accept state. So if I'm in here q sub 1 or q sub 2, these two are accept states. So if my string is composed of the empty string, if my string is an empty string, my machine is going to apparently accept it. However, it's going to pop out of acceptance on either one of the 2 branches when it sees a 0. So when it sees the first 0, it's going to pop out of the acceptance state, and it's going to go to simultaneously to Q3 and Q4. When it's in Q3, if it sees another 0, it goes back to Q sub 1, which is an accept state. So apparently you see that this upper branch is going to accept any string that has even numbers of zeros. And in the lower branch, upon seeing the second 0, it's going to go to Q sub 5 here. So therefore, if the next string is also the next symbol is also a 0, it's going to go to Q sub 2. So this upper branch is going to be accepting strings with even number of zeros. This lower branch is going to accept strings that have multiples of 3 zeros, right? So this branch is going to accept strings in which the number of zeros is going to be a multiple of 3. So, and if either one of these two branches is in an accept state, then your machine is going to accept, which means that it's going to accept either the strings with even number of zeros or the strings where the number of zeros are multiples of 3s. So let's go over a couple of examples, see what happens. Let's see what happens with string 0, 0, 0, 0. My machine starts in Q sub 0, and then immediately it's going to branch into Q sub 1 and Q sub 2. Then when it sees a 0, Q sub 1 branch is going to go to Q sub 3, and then Q sub 2 branch is going to go to Q sub 4. When it sees the next 0, then Q sub 3 branch goes to Q sub 1, and then Q sub 4 branch is going to go to Q sub 5. When it sees another 0, then Q sub 1 is going to go to Q sub 3, and then Q sub 5 is going to go to Q sub 2. And then for the next branch, then Q sub 3 is going to go back to Q sub 1, and then Q sub 2 is going to go to Q sub 4. And since Q sub 1 is an accept state here, then my machine is going to accept this string. How about this string made of 6 zeros, right? So I'm going to start in Q sub 0 and immediately branch into Q sub 1 and Q sub 2 because of the epsilon transition. Then Q sub 1 branch, let's process Q sub 1 branch separately. So it's going to go to Q sub 3, Q sub 1, Q sub 3, Q sub 1, Q sub 3. So for the first 0, for the second 0, for the third 0, for the fourth 0, for the fifth 0, and then for the sixth 0, it's going to go back to Q sub 1. That's an accept state. And then Q sub 2 is going to go to Q sub 4, Q sub 5, Q sub 2, Q sub 4, Q sub 5, Q sub 2, and this is going to accept. Now this is going to accept because both the string has an even number of zeros and also multiples of 3. But apparently this machine is not going to accept a string with 5 zeros because you're going to start from Q sub 0 and immediately branch to Q sub 1 and Q sub 2, and then for the first 0 you're going to go to Q sub 3, for the next 0 you're going to go to Q sub 1, for the next 0 you're going to go to Q sub 3, for the next 0 you're going to go to Q sub 1, for the next 0 you're going to go back to Q sub 3, and that branch is not going to accept Q sub 2. For the first 0 it's going to go to Q sub 4, for the next 0 to Q sub 5, for the next 0 back to Q sub 2, for the next 0 to Q sub 4, for the next 0 to Q sub 5. This branch is not going to also accept. So it's not going to accept this string, but it's going to accept this string and this string. The string with even zeros, or a string in which number of zeros is equal to a multiple of 3. And if your string is neither one of these two kinds, then that machine is not going to accept it. Now, here's a nice little item for you to think about, and I'm going to show a formal proof by construction later on the closure of the regular operations using NFAs. See, this example here shows that if I have two strings, a string with even number, or two languages, strings of languages with even number of zeros, or string of languages with multiples of 3 numbers of zeros, ORing them was very easily done with an NFA, whereas with a DFA it was a little bit more difficult to make it. Although it was possible, it was far more difficult. I had to do cross products of states, and transition function will be a mess and it will be huge, whereas you can kind of, by example, see that the same process showing closure or constructing languages, regular languages, with the regular operations using NFAs is far more efficient and faster than doing with the DFA. So this example, I'm just throwing it out so you'll see as a view of how it works, of using regular operations for languages. But later on we're actually going to prove and construct mechanisms to build regular languages with NFAs by performing regular operations on simpler languages, or the NFAs of simpler languages. So that's an example here for you to see. All right, so let's take a look at this example now. It's an NFA with 3 states. Q sub 1 is your start state and also an accept state. And then Q sub 2 and Q sub 3. With Q sub 1, you have one outgoing transition over B, but you don't have any outgoing transitions over A. However, you do have an outgoing transition with epsilon. Then in Q sub 2, you have an outgoing transition for B to Q sub 3, and then you have 2 outgoing transitions for A. You stay in Q sub 2 or you go to Q sub 3. And in Q sub 3, the only outgoing transition is A. So if you're in Q sub 3 and you see a B, then that ends the string, or rather that ends that branch of computation there. Let's take a look at this and see how this works and how does this machine compute. Q sub 1 is an accept state. That means that the start state is an accept state, so this machine accepts the string epsilon. Let's see what happens with the string A. Does this machine accept string A? At the first sight, it might not seem that your machine has an outgoing transition from state Q1 for A, so that should have closed the sequence of transition for state A. But if you start in Q sub 1 without reading to any without reading any symbol, you take the epsilon transition, which basically means that you go to Q sub 3. So when your machine starts in Q sub 1, it immediately goes to Q sub 3. Okay, so which means that if the first symbol out of this state is Q sub 3, is A, then the state Q sub 3 transitions back to Q sub 1. And so once you go back to Q sub 1, then you take the epsilon transition and go back to Q sub 3. So over every single A that you see, you end up with the possibility of being in an accept state. So if that is the end of your string, then you are accepting the string. So how about a string with 2 A's in it? So a string with 2 A's basically then means that the state Q sub 3 then again over the second A goes to Q sub 1, which is an accept state, and with the epsilon transition goes back to Q sub 3. So Q sub 1 effectively will immediately itself transition in Q sub 3. And so at that point, your machine with the second A is gonna have 2 states, Q sub 1 and Q sub 3, and still Q sub 1 is an accept state. So it's gonna accept this string. In fact, it's gonna accept a string that's made of any number of A's. How about when my machine sees a B? The moment my machine sees a B, if you're in Q sub 1, and you're obviously your machine transitions to Q sub 3, because when you're in Q sub 1 without reading anything, you're in Q sub 3, and over reading a B, you're going to go into Q sub 2. In the Q sub 2, then if your machine sees an A, then it either stays in Q sub 2 or transitions into Q sub 3. So obviously my machine still does not accept BA. But if you add another A, then Q sub 3 will end up in Q sub 1, which is an accept state. And then Q sub 2 over the second A will have a choice of staying in Q sub 2 or branching again into Q sub 3. So this machine will accept BAA, but it doesn't accept BA or BB. Or BAB. In fact, let's just run a simple example here with some strings and see if it accepts it. So let's say A, B, B, A, or rather, let's do this this string. It's probably a little bit more challenging to do. Let's do B, A, B, B, A. So my machine starts in Q sub 1, which immediately branches into Q sub 3. So so I'm in Q sub 1 and Q sub 3 at the same time. Actually, let's branch this out this way. And so the first symbol is a B. So what's going to happen if I see a B? If I see a B, Q sub 3 with a B ends right there. And Q sub 1 with a B will go to Q sub 2. How about when I see an A? With an A, Q sub 2 branches into Q sub 2 itself, or branches into Q sub 3. And then with a B, then Q sub 3 with a B dies, and then Q sub 2 with a B goes to Q sub 3. And then Q sub 2 with a B goes to Q sub 3. And then when I see the next, so I process the first B, and I process the first A right here. Now I'm processing the first B, so that I processed, and now I process the second B. So the second B basically kills off Q sub 3, because Q sub 3 doesn't have any outgoing transitions for B. And so my machine has no states to process, and so when I see the next A, there's no state to process anymore, and so my machine basically processes state A with no states, and so then rejects this string W2. However, with the string BA, let's say W3, being the string BA, so I start in Q sub 1, immediately branch into Q sub 3, and of course I am in Q sub 1. Then in Q sub 3, when I see a B, that dies off there, and with a B I go to Q sub 2. So that's the first B processed. Now Q sub 2 with an A branches into Q sub 2 and Q sub 3. And then Q sub 3 with a B dies, because Q sub 3 doesn't have an outgoing transition, but Q sub 2 with the B goes to Q sub 3. And then finally Q sub 3 with an A goes to Q sub 1, and that means that the string W sub 3 is going to be accepted. So the strings A, B, A, BA are accepted, whereas the strings B, BB, BAB, or BA, BBA were not accepted. So these strings will be rejected, and these sets of strings will be accepted. So this is another simple looking NFA. But as you notice here, the computation of this NFA is a little bit more involving with what we had in the first 2 or 3 examples earlier, because when you have epsilon transitions and when you have multiple transitions outgoing from a state, your machine would have to take those transitions before you go to the next symbol and process it. Whereas with the DFA, it's more of a mechanical process, right? You basically know which state you're in, which symbol you're reading, and which state you end up going to. So it's kind of, NFAs are more flexible, they're more compact, and you can design them much more efficiently. However, recognizing what kind of languages they accept, you'd have to kind of process with them, work with them, run them over several examples, and see what kind of patterns emerge out of NFAs. That being said, later on in this class, in a couple of weeks, we will go, or rather in a couple of units, we will go to show that how you can simplify an NFA and get out of it a regular expression, and how you can use these regular expressions effectively to look at and the languages that those expressions represent. So now we are at the point that we can go ahead and formally define a non-deterministic finite automaton. And before I give you the next example and actually look at computations of a finite automaton, non-deterministic finite automaton, let's take a look at how we can formally define them. The formal definition of an NFA is practically similar to what we had for a DFA. Both have a set of states, a set of alphabet, a transition function, a start state, and an accept state. The difference between the DFA and an NFA, obviously by looking at this definition, is step 3, or rather item 3, which is the transition function. So in the deterministic and a DFA, if you remember, a deterministic finite automaton, we define it as a 5-tuple Q, sigma, delta, Q sub 0, and F, where Q was a finite set of states, sigma was a finite alphabet, delta was a transition function from Q cross sigma onto Q, and Q sub 0, the accept state, one of the states, and F a subset or equal to the set of states, and that would be the accept state. And Q sub 0 was your start state. In the non-deterministic finite automaton, there are two differences in the transition function. So you still have a finite set of states, you still have a finite set of alphabet. The transition function is from the cross product of your states and the alphabet union with the empty string. So the non-deterministic automaton will have the possibility of processing without reading any symbol. That's why we put an underscore sigma or a subscript sigma here. I mean epsilon here, to represent that sigma sub epsilon is basically your sigma that you union it with the empty string. So you will have the empty string as a part of a transition possibility. And the range of your transition function is not one state. It's a set of states. In fact, it's a power set of Q. So formally, a non-deterministic finite automaton is a 5-tuple Q, sigma, delta, Q sub 0, and F, where Q is a finite set of states, sigma is a finite alphabet, delta is the transition function that takes as input a ordered pair from state and a symbol from this alphabet or at the empty string, and it has the option of returning as output a set of state, meaning that when you're in a state, the result of a transition from that state is not going to be just one state, it is a set of state. If you don't have any transition outgoing, it would be an empty set. If you have multiple transitions, it would be a set made of multiple states. In fact, if each set has the possibility of going to all other states, including itself, then you would get into the power set of Q. The Q sub 0 is one state out of the set of states that you have that is labeled as the start state. That's the state where your NFA starts its computation. And F is a set of accept states, which is a subset or equal to the set of finite set of states that your NFA has. So this is the formal transition or the formal definition of an NFA. Very, very similar to a DFA with two differences, and those two differences are effectively in the transition function, is the way that your NFA transitions. Your NFA transitions, let me actually write the DFA, so let's call this delta sub n to denote a DFA, and a delta sub d. So remember, the delta sub d was a transition function from Q cross sigma to Q, but a delta of your NFA is a transition from Q cross sigma epsilon, use your alphabet and the empty string, and it transitions into a power set of Q, which means that it could go to any set made of the original queues. So each outgoing each state may end up into multiple states over a transition, and this is what this power set here denotes. Um, so I'm gonna actually next go ahead and show you an example of the first finite automaton, non-deterministic finite automaton that we discussed earlier, and then I'm going to write it down formally in terms of the formal definition of the NFA, and then I'm going to show you how we would formally then define computation in an NFA.